Okay, so the recording is now in progress, and let me welcome you once again. We are on the second class of our course Communication Networks, and as I said earlier, that we will try to keep this course as short as possible. We will be taking only 20 classes, so already one is over, the second is going on. In the first class, which was an introductory class, we talked about what communication network is about, and I wanted to give you an overview of the whole course. In the course, we will be talking about different wired and wireless communication networks. For example, in wired communication networks, we will be mainly focusing on computer networks. In wireless communication networks, we will be talking about cellular communication, mobile communication, Wi-Fi, and cellular generations. And then we will be talking about industrial communication networks, which will be useful for the next IoT revolution, which is called IIoT, or industrial IoT. Which is more or less aligned with Industry 4.0 and beyond. In last class, we just talked about the definition, communication network. So I will just write the name once again. Communication networks. And we talked about some definitions, some ideas which might come to you when you hear this term communication networks. Today, let us have a deeper look. We try to consider the basic constituent blocks of a communication network from an abstract level. That means although the communication networks might seem very different from each other, we might be using one communication network right now, sitting in front of your laptop or mobile or something. Then probably you'll be switching to another communication network when you probably communicate over a telephone, or probably something else when you watch a TV via dish TV television. So all of these are communication networks, and they look very different from each other when you see from device perspective, like the gadgets or the devices that you are using, or the cables that are connected with them, or the links that might be serving them. So they are all very different when you look at them from the physical perspective, or how they look like, how the device constructions are. But in our course, we are trying to abstract ourselves from this particular device type of view. Rather, we will try to have an abstract view. In the abstract view, in any communication network, we have actually two basic entities, the nodes and the links. And these nodes and the links make every communication network. So these are two very generic terms. Nodes and links, and they made up all type of communication networks. The nodes may differ, the links may differ from each other, and that's why every communication network looks different from each other in terms of their size, capacity, type of information they are carrying, and so on. But every thing or every communication network can be broken down into basic nodes and links. So in the last class, I also probably gave you an example that in our EC department, suppose we have a color laser printer and we wanted to put it on network. So that is obviously a simple communication network that we wanted to form. And in that network, the nodes are the PCs and the laser printer and so on. The links are the Ethernet cables that run through the PC to the printer and so on. So in this way, or maybe probably you have last night you have watched a television show where you have got the signal from your dish TV, which is probably placed on your rooftop. So that dish TV module is also a node, and the satellite which is serving to you is another node, and the link between satellite and your dish TV antenna is a link. So based on different prospect or applications, the nodes or links may change, but everything can be boiled down finally to nodes and links. Now, when we consider a communication network in terms of nodes and links, they have to be characterized on the basis of their actions. What I mean to say is, suppose a communication network looks like this, a simple 3-node network, where this is node number 1, this is node number 2, this is node number 3. Now, what I want to transfer is some information from node 1 to node 3. But suppose there is no direct connection between node 1 and node 3. There is a connection from node 1 to node 2 and then from node 2 to node 3. An example, well, if I go back to our laser printer case, the node 1 may be the PC, which is probably kept in one of the professor's room. Node 3 might be the color laser printer, and node 2 is the switch or hub box, which is placed over a wooden box on the corridor, which is have some green light blinking. So that is probably connecting these two. So now in this setup, the PC, which is node 1, is generating some information. Probably you want to print something, a color print action, which is being generated at node 1. Node 3 is obviously carrying out that instruction, so it is consuming the information. So it is taking the PDF page inside it and printing and goes on printing the page. But node 2, which stands in between, does not directly generate the information, neither consume the information. So node 2 is something like in between, which will be always there facilitating the exchange of information from one part of the network to other part of the network, but it is not the ultimate generator or ultimate consumer of the information. So from this particular point of view, we can have two different type of nodes. The first type of nodes are called terminal, and the second type of node is called communication. So we have two type of nodes in any communication network. Some are terminal nodes, rightly said so, because they are at the end. So node 1 and node 3 both are terminal nodes. They can be written as TN1 and say TN2, something like this. And node 2 is situated in between, which is taking the information from one part of the network. This is the part of the network I'm talking about, this part of the network, to this part of the network, but it does not consume or generate the information. A similar example is a telephone exchange. When you are calling to some person, your call is going through a telephone exchange. So your phone is a terminal node. Your friend's phone who you are calling to is another terminal node, but the telephone exchange in between is only facilitating the exchange of information. So it is not generating or consuming the information, and it's a communication node. So the communication nodes are like the Wi-Fi routers, switch, hub, telephone exchanges, mobile switching centers, which are in cellular mobile communication. Then there might be some repeater nodes in optical fiber network under the sea, and so on. Now in communication networks, our major focus will be understanding these communication nodes, how they behave, and how they should be connected to form a big network. So that's the first part of our discussion today, that is about nodes. Now, once we are done with characterizing different type of nodes, let us take a look at the links. The links are between the nodes which make the network. Now, the links can be also characterized in different ways. The most layman kind of approach is to look at the link and say how the link looks like. If you look at the link and see that there is a cable, then it's a wired link. That means there is a wire. Now the cables can be also of different types. We have power supply cables in our home, which is connected to a tube light or a fan. They are probably the simplest type of cable one can think of, but they are not very good in carrying information. They are good for carrying the electrical power supply, which is most of the time 50 Hz signal. So that is possible through them. But when you want to send a higher amount of data or higher amount of signal in terms of quantity of information, then you generally go for coaxial kind of cables. The coaxial kind of cables you can find out when you have a cable television. Suppose you don't have a dish TV connection directly to your home. What you do is you take a cable connection from your local cable TV provider. Then probably a black cable is coming to your home, and then probably there is a set-top box which is connected via the black cable. So I'm talking about that black cable. That is a coaxial cable. So those coaxial cables are a bit better than the electrical cables that are used for general electrical wiring, in terms of they are capable of carrying much more information. Now, when we cannot even cope up with those cables, then we go for optical fiber cables. Well, optical fiber cables are generally put in a big campus like ours. We have optical cables running all around because we need to access a huge amount of data in different departments, hostels, centers, administrations, and so on. In metal cables, the signal travel through electricity, and the electrical signal changes carry the information. How? Well, most of the time we send electrical pulses. Electrical signals go up and down, and thereby denoting ones and zeros. So you need to switch it very fast, having ones and zeros and so on in a very fast manner so that you can send a lot of data. So that is how the electrical signal propagate through metal cables. By metal cables, I mean the twisted pair cables that we use for electrical wiring, or the coaxial cables and so on. However, when we consider optical fiber cables, then the signal travels through them through light. And how light is traveling through an optical fiber cable, probably you know about that as well. Well, in optical fiber cable, we have two glass cylinders, concentric. So the inner glass cylinder is of higher refractive index. The outer glass cylinder is of lower refractive index. So it's, if you take a cross section, it will look something like this. So there is a inner cylinder and there is an outer cylinder. Now the inner cylinder has a higher refractive index, the outer cylinder has a lower refractive index, and when you send a light signal from higher refractive index material to a lower refractive index material, then there exists a critical angle at which if you send the signal, then the signal will not go to the second medium, rather it will be completely reflected back to the first medium once again. So that is how probably you know the signal propagate from water to air and so on. Probably have read it in your +2 physics. So that same idea applies here. So when you send a signal at that critical angle, the signal does not leave the inner cylinder and the signal gets reflected totally. It is called total internal reflection. So via this total internal reflection, the light signal propagates along the inner cylinder. So the losses are very low and the signal can propagate to a very, very large distance. So this is the idea behind optical fiber cables. And due to these optical fiber cables, actually you are now probably browsing a page from a place as far as US or probably Canada. We have very long cables which are spanning the whole globe, and that is carrying the most of the internet traffic nowadays. It's not satellite, it's optical fiber cables. And how long the cables are? Well, if you consider a cable which is the primary provider of internet to India, that is called CME-V3 cable. More on this probably if we can get time. So that cable runs around length of around 40,000 kilometers. So it starts from one continent, Europe, and then it goes through Asia, and then it goes all the way to Australia. So these are different type of links that we have, but this kind of link characterization from the physical perspective is very naive, because we look at the construction of the cable and then say that, okay, this is one type of link, this is another type of link. For communication network study, generally we prefer a more abstract point of view, from the functionality point of view, just like the nodes. These nodes, as I said, can be PCs, can be fax machines, can be a mobile phone. So we are not looking at the nodes from the physical point of view, rather we are looking at them from the functional point of view, whether they are terminal nodes or they are communication nodes. Similarly, and sometimes these nodes can interchange their role. For example, if you are using your mobile phone in the hotspot mode, suppose you have got an Wi-Fi connection, but the Wi-Fi connection is disrupted. So what you do? Okay, your mobile phone has a data connection, so you turn your mobile phone into hotspot mode, and then you can access from laptop through that mobile phone. So in that case, the mobile phone is not a terminal node anymore. It is becoming a communication node, and your laptop, which is probably taking the information from the mobile phone and probably using it, becomes a communication node. Sorry, becomes a terminal node. So the mobile phone becomes the communication node and the laptop becomes the terminal node in hotspot kind of mode. So that's what I was talking about. Like from the functional point of view, we can divide the nodes into two types. Similarly, from functional point of view, we can divide the links into two types. One is point to point, The other one is shared. Now, what do we mean by point-to-point and shared? Now, to understand point-to-point links and shared links, I need to draw an example network and probably give you some idea of how these two type of links differ. Well, first of all, let us understand the idea that shared links concept came much later. And in this diagram that I'm going to draw now, I will try to tell you how the things evolve and how people understood the importance of shared links. Well, let us consider a network with, say, 6 nodes. There are 6 nodes that needs to be connected to each other. An historical perspective, this was the case when early days telephones were invented. When telephone was invented in 1876 by Alexander Graham Bell, soon it became quite a hit, mostly among the upper layer or upper class of a city or of a citizen council. The rich people, the important people knew the importance of communicating voice to each other, and they started installing telephones to their home. So the next problem was the telephone was fine, that there was a mouthpiece and there was a earpiece and they were connected via a device. So that was one invention. But the next set of invention that was being demanded was how these telephones need to be connected with each other. Now, suppose there is a city where we have a mayor and then there are some barons or something. So there are 5, 6 people, important people who have got the telephone. I'm talking about 1880s, 1890s, something like that, in that time range. So they have got the telephones in their home. So they need to be connected with each other. So the first thing they thought about, okay, fine, let us connect everybody with everybody else. So there should not be a situation that the mayor cannot talk to the baron or baron cannot talk to the duke or something like that. Everybody should be able to contact to everybody else. So the initial days connections between telephones was something like this. So probably you can figure out how many lines are required and how quickly the number of links are becoming very high. So if I have in a city, suppose n number of telephones, can you tell me how many such links we need to form a network like this in the chat box? So my query to you is, suppose we have made a have to make a telephone network. Remember, I'm talking about the early days where telephone was the only means. Forget about data, forget about anything. It was only voice being communicated. And suppose in one city we have n number of such telephones, and we need to connect everybody with everybody else. Then how many such links we need? Please write your answer in the chat box. And please remember, this chat messages, everything are being stored and will be used to evaluate your content assessment and other things. Okay. So Bedos Shruti is saying that n minus 1 for one person, isn't it? I'm talking about all the number of links that have to be constructed by the city council or something. Suppose you have 6, then do you see only 5 links on the board? I guess no. Probably you need to modify your thing. Okay, Pranit is saying NC2 and Nilabro is saying so. And Akash and Soikot. Right. Right. So the idea is that everybody needs to contact to n minus 1 number of people. And there are n such number of people. So basically for n nodes, what you need is n into n minus 1. considering that the links are unidirectional. That means the links can carry information in one way. But if one link between A and B is sufficient, that means you can carry information from A to B. Suppose this is A and suppose this is B. So this one link is sufficient in this direction as well as in this direction. Then I can divide this by 2. So which is probably you have rightly wrote as NC2. So that's the idea. That is, when you have n number of nodes, then you have roughly you have exactly this number of links that needs to be constructed. Well, roughly, when you consider n is very large, by very large we mean thousands or some, even larger, then the difference between n and n minus 1 is almost negligible. So you can say that this is proportional to n square. So I'm just trying to give you an idea of the complexity of the network. Probably there are computer science people here, so they know about the complexity of an algorithm or something. It's like if you have a for loop and then you have nested for loop and then you have a nested for loop, then the complexity becomes cubic. If you have two nested for loops, the complexity becomes square, something like that. So in network also, we have similar kind of thing. If you have n number of nodes, then the complexity of the network increases, considering the number of links increases with proportional to n square. Now, when n becomes larger, n square becomes even more larger. And soon, if a city is growing, like suppose they had 5 telephones, and then next year they have 10, next year they have 100, next year they have 10,000. So soon, the number of connections becomes prohibitively large. Not only large, prohibitively large. It is very difficult to construct so many lines. And that was actually the case in the early days of telephone communication. If you look at the telephone poles, I don't know if you have seen landline telephone poles or not. Probably you have seen some abandoned, because landline telephones are almost abandoned nowadays. But and most of the cables are running underground. But if you remember old days telephone poles, the telephone poles were not quite large. But in the early days, the telephones were quite large because they have to carry so many wires. I still remember from a 1920 Chicago picture that there were 18 people standing on a telephone pole. It was constructed by a very big oak tree, so you can consider how many lines it was carrying. So that was the case in the early days of the network, when people were trying to connect everybody with everybody else. And that is what we call P2P, or point to point. This is one point, this is one point, all are terminal nodes. There is no concept of communication node. Every terminal node needs to be connected with every terminal node. So that's why the number of links is going in a huge manner. But then people thought that this approach is not scalable. We often use the term scalable or scalability. The scalable here means that if certain solution is applicable in a small area or a small project, can we make the same solution for a bigger project? Well, this approach is not scalable because it is good for 5 nodes. It is not good for 5,000 nodes. So we have to think about something to have a scalability. Then people say that, okay, let the nodes be like this. And here, suppose the node be like this. And suppose this is the western part of the city, this is the eastern part of the city. Let us divide the city into 2 zones and let us make 2 exchanges, telephone exchanges. So let us make a communication node 1 here, let us make a communication node 2 here. And instead of trying to communicate with everybody, let us connect to this central node or communication node in this way, and let us communicate among these communication nodes. So what we have is something like this. Now, where we are not trying to connect everybody with everybody else, rather we are making zones, and in each zone we make a communication node. That communication node takes care about the connections in that zone, and here something like this. So how the communication takes place? If TN1 wants to connect to TN4, they have to follow this route, this route, this route. If TN2 wants to communicate to TN6, then this route, and so on. If TN2 and TN3 wants to communicate via this, something like this. Now, what are the advantages of such kind of grouping? First of all, many connection requests can be solved in a local manner. Well, that's why you have something called local calls. For example, we have landline telephone network in NIT Durgapur, and there are a lot of internal telephone calls. Like the HOD of mechanical engineering department wants to discuss something with HOD of metallurgy department. So in these kind of calls, the connections, the request, everything should not be public to the whole world. They can be contained to NIT Durgapur itself to minimize the traffic flow. So that's what is first possible. That is, when TN2 and TN3 wants to connect to each other, and suppose this CN1 is the exchange in NIT Durgapur. For example, if you want to see the exchange in NIT Durgapur when you come back to the college, I hope you will be soon coming back to college, because the government has already issued order, and I have seen today that already the hostels are being open for PG and PhD. So I hope soon it will be open for you as well. Anyway, that's not beyond in my hand, so I'm just giving you some information. Anyway, so when you come back to the campus, when you are in the main administrative building, there is a block called telephone exchange. So there is an exchange. So when the HOD of mechanical engineering department makes a connection request, it goes to that exchange, then comes back to the metallurgy department. So it is solved in a local manner here only. Similarly, something else. But when suppose the head of mechanical engineering department wants to talk to CMERI person, a researcher in CMERI, then that person connects the exchange in NIT Durgapur. NIT Durgapur connects to the exchange of CMERI, and then CMERI person or exchange connects to the corresponding CMERI person. So then only it leaves the local kind of barrier, and then it goes to a regional or a city-wide kind of region. And obviously, this network is a very simplistic network. When you consider the whole country or the whole state, it is much more involved and much more complex. I'm just trying to show you as if in the whole world there exist only two campuses, NIT and CMERI, and then the whole communication is between them. So I'm trying to simplify the situation. Anyway, going back to our original problem, that we had lot of links that can be solved now, because here if you see the complexity of the network or the number of links that we probably require is of the order of n. If you have n number of nodes, then you have around n number of links, more or less. So that is kind of scalable. Like every new node, one new link. That is probably kind of scalable. So this kind of approach, when we move from point to point to this kind of approach, makes our network much more scalable, much more realizable. However, here is a concept called shared kind of link. What is shared link? Well, you see, there is a connection between CN1 and CN2. Now, suppose TN1 is talking to TN4. TN1 is talking to TN4. So which line is being engaged? This line, and this line. So the line between CN1 and CN2 is now being engaged. So that line is going to be used by some other person as well. Like when TN2 wants to talk to TN6, then the same line is being used. So the link between communication node 1 and communication node 2 is not a private property of two entities. It is being shared by all subscribers in the network. So that's why we use the term shared link. So in the previous case, this link is dedicated between A and B. So this link is always between Baron and Duke. Nobody else is going to enter into that territory. However, in shared kind of link, everybody can probably use this common shared link. Is there any con? I'm only talking about pro, that is advantage. Is there any disadvantage for that? Can you figure out any disadvantage of this kind of scenario? Like when we have shared link, obviously the advantages are quite straightforward, that we have reduced the number of links, we have made the design much more easier, scalable, and easily implementable. But what are the problems? Okay, Mohit is talking about central point of failure. This is obviously one very interesting point. That is, if suppose this link does not work, then at least these links work, so it does not affect the whole network. Here, if this link does not work, then the whole network goes down. That is the point. But if suppose even if we do not have a failure, what immediate inconvenience one might feel, which was not here? What Mohit is saying, of course, is relevant. But even without failure, we yes, record P2P. I'm looking at your chat. Anything else? Record other than P2P? Or anybody else think about any potential problem in this design? Okay, so Mohit has come up. There might be delays causing to queuing of network calls in the conversation node, loss of privacy and engaged. Yes, I was trying to look at this term, and obviously the privacy issue. I'm coming to that privacy issue, but this engaged, this term itself is a very interesting term. Like when you call over phone, sometimes you find that all lines are busy. So this is the reason why this kind of term, all routes are busy or all lines are busy, that became so popular. The idea is here, when this node, suppose this is TN6 and this is suppose TN4. When TN6 and TN4 wants to talk, there is always a dedicated line between them, which is never shared to anybody else. So you are not at the mercy of any other subscriber, whether they are talking or not. And you can always use this line between yourselves. So there is no concept of blocking. There is no concept that you are not being allowed to make a call or you make use of the resources. But here, if suppose there is only a single line between CN1 and CN2, let us assume, then suppose TN1 is talking to TN4, then at the same time, if TN2 wants to talk to TN6, then he or she will find the answer from the network that all routes are busy and we cannot take your call right now. Okay, there are two things. First of all, generally we don't use a single line. We have multiple lines, but even with multiple lines, there might be certain problems like this. Why still such a network works? Because we are never busy for 24 hours over a telephone call, and there is a very low chance that two simultaneous calls will be generated at the same time. So obviously there are chances that the people will find that the lines are busy, but probably the inconvenience they get is not as big as the convenience of reducing the number of links. So that is first point. That is point number one, that obviously there is a concept of blocking, but the blocking probability is generally not very high. We are engineers, we want to talk in terms of numbers. So if you want to know what is the exact blocking probability that we follow in India, it is something around 0.002. So this is something like a typical blocking probability that we face while making calls in India. Obviously, in other countries or in different exchanges, even over India, this probability is different, because when you consider a rural exchange, for example, where the revenue is not very high, you intentionally make this blocking probability higher because you are losing a lot of revenue there. On the other hand, when you are making an exchange for Bombay stock market or something, or nearby area, then you know that such kind of delays can cause a huge amount of financial loss, and there probably you reduce the amount of blocking probability by using more resources, more advanced network technologies. Anyway, so the first thing that what Ohana was talking about is engaged. I hope she is referring to this kind of thing, that the lines are engaged. Yes. So that is the concept of blocking is always there with sharing. Whenever you are sharing the same resource with others, there is a possibility that the other person is using the resource and you are barred from using that resource. So that's the concept of blocking, which is inherent here, which is obviously a con side or disadvantage. Obviously, there are other things like breach of privacy and this kind of thing. However, if we use end-to-end encryption and other kind of thing, we can solve that part to a little time. Now, it depends on how advanced your technology is. But if we assume that the end-to-end encryption works well, then probably that problem can be solved as well. However, no code is ultimately secure, and even with a dedicated link, probably there is a possibility. But of course, the possibilities are less. Now, when I was talking about P2P links and shared links, you might ask that is the case that the P2P links are over? Like, don't we use P2P links anywhere? Of course not. We use P2P links. Let me talk about that. Now, P2P links are sometimes known as hotlines. So probably you have read in some newspaper somewhere that the two prime ministers are talking over hotline or something like that. Well, the important people, when they are talking to each other, when it's a matter of policy decision, like there's a nuclear conflict, for example, and the North Korean president wants to talk to US president and he finds all lines are busy, that's not obviously a very nice condition. So when you are communicating with very important people, then you generally make provision within the network of having such kind of hotlines or direct point-to-point lines where no such sharing, blocking or something is probably tolerated. Similarly, you both Praneeth and Nilabh have talked about privacy. So in defense and other places also, you have such kind of hotlines where you have dedicated lines. So P2P lines are dedicated where two terminal nodes own the link completely. On the other hand, in shared kind of network approach, the link is generally between two communication nodes, and the link is not owned by a pair of nodes. Rather, it is shared by everybody. The advantage of shared links is that you can make a network with a lesser number of links and make a public network. So this is for public networks like telephone, cellular, and so on, and internet and so on. So in this kind of cases, you can make it bigger, you can make it scalable, which is not possible in this case. But with shared links, you have a concept of blocking and breach of privacy and failure propagation, as Mohit was earlier told. So those kind of situations are avoided in P2P links. So P2P links are being used in very important mission critical scenarios. Also, when you communicate very important communication nodes, normally you have P2P links. The idea is, suppose we have everything shared in one country. So there might be situations like somebody is calling from Delhi to Mumbai, and that's why the calls from Chennai to Calcutta are being blocked. So that is very, again, not a very nice scenario to deal with. So what happens is that the major exchanges or the major communication nodes are also sometimes connected via P2P links. So they have direct communication between them. So the summary of the thing is, when you have nodes which are not active for all the time, like your telephone, probably you talk over phone for say 1 hour in 24 hours, not more than that. So for those cases, probably you can go for the shared kind of links because sharing is possible. But when you are talking about nodes which are very busy in a network, then probably you should go for P2P kind of links, and which may be the case for the servers and the exchanges and so on. Now, finally, I would like to close this class with something called value of a network, and then we will continue in our next class with evolution of communication networks. So before I talk about value of a network, let me quickly summarize what we studied today. We studied today the major constituent blocks of a communication network. There might be nodes, there might be links, and from a functional point of view, you can have terminal nodes or communication nodes. Terminal nodes are generator of information. Communication nodes are the facilitator of exchange of information. Similarly, you can also have different type of links. From the functional point of links, you can have point-to-point links or you can have shared links. both have their advantages and disadvantages, and I have told you how to design a network. A network might have both type of links, point to point and shared. Shared links are probably for those nodes which are not very busy, and point to point links are those nodes which are important and probably very busy. So both these designs coexist with each other. And finally, I talk about value of a network. Well, I was talking about so far about the physical links or connections, but there might be logical links as well. What I mean to say is, you are using probably your phone, and your phone is being connected to the nearest mobile tower. So there is one link between them, but over the same link, you are sometimes using the connection through WhatsApp, sometimes using the connection to do email, sometimes you are probably watching YouTube. So you are making several connections, and sometimes simultaneously as well. So there are a lot of logical connections between nodes as well. Now, when you consider such logical connections, depends on the type of the application, what is the value of the network. And there are certain laws which are kind of like very famous for assuming or considering the value of the network. The first law is Sarnoff's law, which tells that the value of the network is proportional to the number of nodes, n. Now, where such kind of situation arises? Well, if you're using a Google group, for example, then the Google group message and everything goes to everybody else. So this is a simple broadcast kind of thing. When you have a broadcast network, suppose you have Yahoo or Google group or something like that, then the Sarnoff's law is valid. That is, if there are n number of users, then the value of the network is directly proportional to n. You have more users, then probably the value of the network becomes larger. It's like YouTube subscribers. You have more subscribers, then you are more valuable, something like that. So that's Sarnoff's law. Then there is another law called Metcalfe's law, where the value of the network is considered to be n squared. Now, this is applicable to something else. Here, we are talking about peer-to-peer, So peer-to-peer networks. What are peer-to-peer networks? Well, one example is FB, or as you now call it, Meta or something. So in Facebook, what you have is you not only have subscribers, but these subscribers can talk to themselves as well. So there are n number of people, but this n number of people can talk to themselves in between. So there is something like n square is the value of the network. And finally, we have Reed's law, where the value of the network is 2 to the power n. This is valid for group forming. What I mean by this is, let us take an example, WhatsApp. In WhatsApp, what you do is, you have WhatsApp, fine, but you can make a group with your friend, you can make another group with that friend and 2 more friends, and so on. So whenever you have any 2 people, they can form, or the number of groups can go on like this. So that's why it is much more exponential and 2 to the power n. So depending on what kind of application you are realizing over a network, although the logical connection, the physical connection I showed, they are following this kind of P2P rule, like n square and n, but the value of the network can be even more. Like at the basic, it is which is related to n, but we can have n square when you have peer-to-peer, like everybody is communicating with everybody else. So it's like P2P kind of case, but in a logical case. And then you can have further group forming, like here we have suppose 25 students, and then 2 of them form another group, and that person forms with another group, and so on. So many groups are there. So we can have something kind of. So with this, we finish today's class with the value of network. We are already on the top of the hour. I'm stopping the recording.